Right, good morning ASs. We're going to look at the series chapter which we started the other day, and I'm going to start on page 230, introducing you to some ideas about a series of numbers. So you can see that they give us a sequence there of 1 plus 2 plus 4 plus 8 plus 16, everyone doubling. Okay, and we're now, instead of just having a sequence of numbers 1, 2, 4, we are actually adding them up. 1 plus 2 plus 4 plus 8. So this is what we call a series. Okay, when we take a sequence and we put plus signs and we add them up together, we can get a finite series. This one over here, for example, is finite for 4 terms. Okay, but we could also do the following. We could say plus, and we could just go on and on and on. Okay, because numbers don't end, so then we would get an infinite series, and we might be interested in adding up an infinite set of numbers. We'll talk about that a little bit later. Okay, so a series that continues indefinitely is called infinite, and a series that has a finite set of terms or an ending to it will be called a finite series. Now, one of the ways that we want to write this is we're going to use what's known as sigma notation. This is the Greek letter sigma, and it basically means the sum of a series of terms. Okay, now we already saw that this sequence over here could be written as 2 to the 0, which is our 1, plus 2 to the 1, plus 2 to the 2, etc., etc. So if I wanted to write an infinite series like this, then I would write this as 2 to the r, okay, where I could put r as going from 0 to infinity, okay? Or if you wanted just a finite series or something like this, 1 plus 2 plus 4 plus 8 plus 16, that would be from 0 to 4. Okay, and would get you 5 terms. Okay, so this notation of sigma, okay, literally says the following. It says, give me the sum of terms for 2 where r starts at 0 and ends at 4. And that really is the same as this series over here. So sigma notation is going to be an important way of writing down some of these numbers, okay, or some of these series. In the textbook, they give you another example there, and I'm just going to do that one as well. They give you 1 plus a half plus a quarter. Okay, 1 plus a half plus a quarter plus an eighth, and it goes on and on and on. So this is one of those ones that is infinite. And they say, let's write that in sigma notation. Well, again, we can write this as the sum of all the values which are half to the r, where r starts at 0 again and goes up to infinity. Okay, there it is. Okay, so half to the 0 would be the 1. The half to the 1 would be a half squared would be a quarter, half to the 3 would be an eighth, and so on and so on. So that expression gives you that entire sequence, okay, or that entire, should I say, series, okay. Now, okay, I'm going to ask you a question about this series. It's not in the textbook, okay, but what would the sum of that series be? Well, let me illustrate it like this. Here is a square, 1 square. Okay, if we add on half a square, I want to make another big square over here. Okay, let's make that a little bit neater. Let's make it on this side. Okay, but that's going to go into my picture, so I'm just going to move that over a little bit. Just give me 1 sec. Right, let's move that across here. Okay. So we've got 1 whole square. Let's make that equivalent to the 1 over there, okay? Now we've got to add on our half a square, all right? So there's half a square, okay? Then we've got to add on a quarter, so let's add on a quarter. Then we've got to add on an eighth, that's an eighth. then a 16th, that's a 16th, then a 32nd, that's a 32nd, then a 64th. And all we're doing is adding on just a little bit every time. Now we'll keep making these little blocks smaller and smaller and keep shading in and leaving one out. Okay, and as we go on to infinity, what is the final sum of this sequence or this series of terms? What is the total addition? Well, I'm sure you can see from this picture that it will never go beyond 2, because there'll always be just this little bit amount just not shaded. But look, it's covering more and more of that second square as we keep going. Okay, so to infinity, the ultimate end, if you want to, which doesn't end, if I can put it that way, okay, you would never get past 2. You can't. Okay, you would always stay within the boundaries of 2. So the sum of this sequence from 0 to infinity is simply the answer 2. Okay, it's amazing that you can add an infinite amount of things to get a finite answer. Okay, if you end that sequence, you'll always be shy of 2. But if you get to infinity, then you've got 2. So 2 is the ultimate answer for that sequence. So there again is a series of terms that adds up to a finite value, even though it is an infinite series. That's something that we're going to discuss a little bit more in a few moments' time. Now, in example 19b, and I'm going to take you through this one, okay, they then say, let's write the following series in sigma notation. So what do we have here? We have a 1, then we have a minus x, we have a plus x squared, then we have a minus x cubed, plus x to the 4, minus x to the 5, etc., etc., and we keep going. Okay, so how are we going to write that in sigma notation? Well, we can certainly see that we've got an x to the r here, where r would start from 0 to infinity, again, if we just kept going. Okay, because x to the 0 is 1, but x to the 1 is not minus x. Okay, so what do we need to do here to create this minus and this plus? Okay, well, we can also multiply by minus 1 to the r. Okay, because minus 1 to the 0 would simply be the 1, but minus 1 to the 1 would make a minus sign in front of the x to the r, okay, and make it minus x. But minus 1 squared would be a positive again. So you can see that the minus 1 to the r also changes those signs to plus and minus as we're going. Okay, and they've taken you through that one. I'm going to encourage you to look at number B's example there, and then you can try writing the sigma notations for exercise 19b number 1 as well as number 2. I'm not going to do those now, but you can give those a try. Then over the page over the page there is exercise 3 as well, which asks you to explain which certain terms that they are looking for there. Okay. So that's the idea of series and writing sigma notation. Okay, now we are going to look in this course mainly at 2 types of series, and the first one is what we call an arithmetic series. Okay, arithmetic. Now you came across some of these before, you've seen them in IG, but you probably weren't told what they are. All an arithmetic series is a series that has a common difference. Okay, so if I take the numbers, for example, let's take 4, then 7, then 10, then 13, you can see that to get from the one number to the other, I have the same value between them. So that if I said 7 minus 4, I'd get 3. And if I said 10 minus 7, I'd get 3. And 13 minus 10 is 3. The difference between each successive term is the same as the last one. So that's what makes it an arithmetic sequence. Okay? So let's write this then, okay, and say that if this 4 was called A, okay, and this 3 was called a D, then what would the 7 be? Well, you can see that it is A plus D. And the 10 would be A plus D, or A plus 2D. And the 13 would be A plus 3D, okay? And so on and so on and so on. So in arithmetic progression, must start with some value number and have a series of common differences to create the next term in the series. Okay. Well, if we went on, okay, until we got to our last term, whatever that last term is, the nth term, okay, do you see that the last term would be a plus, and it would be n minus 1d. Why minus 1? Okay, well, remember, we started with an a, which was a 0d. That was term 1. So term n, okay, this is term 2, which had 1d. Term 3, which had 2d's. Term 4, which had 3d's. Every time the term number is 1 less, so the nth term must be 1 less d term. So n minus 1d. Okay, and that would be the entire arithmetic progression. So if I asked you what is the 100th term, you would say it was a plus 99d. Does that make sense? Okay, so that gives us what an arithmetic sequence looks like. Now we're going to be interested in what the sums of these sequences look like. So I'm going to do that, which comes on the next page there, the sum of an arithmetic progression. Okay, so let's have a look at how an arithmetic progression goes. If we take a plus the next term, which is a plus d, and we go a plus 2d, and eventually we add up a plus n minus 1d. Okay, there's my entire arithmetic progression. Now I'm going to do something interesting now. Okay, I'm going to say, all right, we can add all of those things up, okay, but that's a lot of a's. We don't know how many at the moment. It will be n, okay, but let's see if we do the following. What I'm going to do is I'm going to rewrite that entire sum expression, because that's the sum of my nth terms, okay, that's the sum, or sigma if you want, okay. Let's rewrite this expression though, but start backwards. So then we'll go a plus n minus 1d and plus a n minus 2d. We're going backwards now, okay, and so on and so on. We'd eventually get at the last two terms, we'd get a plus d, and lastly just plus a. Okay, now if we add these two things together, so on this side we'll have two sums, okay, two sums, double the sum that we would have had. We'd add a plus a, which gives me 2a, and then we'd have n minus 1d. Okay, and then we add this a plus d and this a plus n minus 2d, and we'd get another 2a plus n minus 1d. And we kept going all the way, and you can see even at the end here, you've got a plus n minus 1d, which is again 2a plus n minus 1d. So the sums of these additions in every order, no matter how many of them there are, is always the same. And how many terms are there in the sequence? Well, there's n terms. We don't know how many we get. So what we get is that 2sn must be equal to n times 2a plus n minus 1d. Right, let's move this up a little bit so you can just see. So 2n minus 1d, right. And that means that the sum expression, which is the thing we really want to know, is then just n over 2. Okay, we're going to divide that 2 over here. N over 2, 2a plus n minus 1d. Now that is known as the formula for an arithmetic progression. So any arithmetic progression that has any number of terms, finite or infinite you can put in, okay, will have a sum expression where you have the n, which is the number of terms, a, which is the first term, and d, which is the common difference. And if you know those values, you can solve for the sum of the numbers. We're going to see how that works in a moment. Okay, I just want to point out one other little thing about this expression, because one of the things I can do with that same expression is write it as Sn is n over 2. I can take this 2a and split it into a and then plus a plus n minus 1 d. Now, if you know that a is the first term, you also know that a plus n minus 1d ended up being your last term. And so another way of expressing this series is that the sum is n over 2, the first plus the last term. So if you have a finite sequence and you know the first term, the last term of that sequence, you can just put those numbers in, take the number of terms that the sequence has, and that will be divided by 2, multiplied to your first plus your last term, and you've got the total sum of the expression. Well, that literally gives you everything up to page 233, and then there are some examples we're going to have a look at, and you can try exercises from 19C. Okay, so that gets you quite a bit of work to do. Okay, and they go up right up to number 13. Now, I'm just going to do one example. It's not in the textbook. I'm going to just use my own example because we can just do that. Okay, so let's use these expressions and see what we would end up getting. Okay, so let's say the sum of 2n plus 3 from n equals 1 to 8. Okay, what would that generate as a sequence? Well, if I put in 1, I get 2 plus 3, which is 5. And if I put in 2, I'd get 4 plus 3, which is 7. And if I put in 3, I get in 9, and so on. 11, 13, 15, 17, 1, 2, 3, 4, 5, 6, 7, and we've got 19 for the 8th term. Okay, so there's 1 to 19. Now, what would the sum of that expression be? Well, looking at my sum formula, which you've just seen just above here quickly, okay, we know that there are how many terms in this sequence? 1 to 8, there's 8 terms. So the sum of the sequence would be 8 over 2. The first term there is an a, which is 5. Okay, that's my first term of my sequence. My last term is 19. Okay, that's using the first and the last. Okay, so it's 8 over 2, which is 4, 5 plus 19, which is 24. Okay, and 24 times 4 happens to be 96. Well, you can go and test on your calculator if that all adds up to 96. Okay, if I use the first version of the formula, the one that we see over here, where n over 2, 2a plus n minus 1d, let's write it down. Sn equals n over 2, 2a plus n minus 1d. Right, so we know that our n is 8 again, so it's 8 over 2. We know that 2a will be 10 because the first term was 5, so that's 10. Okay, and n minus 1 would be 7. What is the difference between each one? It's 2, it's 14. So the 10 plus the 7 times 2 is 14, that's 24. And again, it's 4 times 24, comes out to exactly the same thing. And of course, you shouldn't end up with two different things. Well, that takes care of arithmetic sequences. Okay, the next series will be that we will look at geometric series or geometric sequences, and we'll see how those get added up in a while. But just go and practice these. You've got 2 sets of exercises to do here. That should keep you busy for a little while. Enjoy the rest of the day, and I'll chat to you again soon.